All right, so done with the quiz here for today. A couple things to note. I haven't quizzed this class yet on the geometric interpretation of mean and median, for example, on those density curves. The mean is the balance point, the median as the point of half the area to the left of the median and to the right of the median. I could in a future quiz, maybe in some future section I have already quizzed, but I haven't for you guys. That's an example of something that could be done. I also think probably next time I might also quiz you on something related to that first PowerPoint and the learning strategies that I have not quizzed you about yet. So go back. It's worth always going back and looking at those learning strategies anyway. Okay. So far the quiz question is focused on not memorization. What's the word? Retrieval practice, that's the word. Okay, so far it's focused on that, but there are other terms in that you should also look at before the quiz next time. I'll probably remind you over email. So we ended lecture A looking at this graph, at the relationship between daily calories and life expectancy, and what we said is it's a positive association. Now, here comes the really tricky part. What does that positive association mean? And what might it not mean? At face value, somebody I think already said it. It seems to mean, was it you that said it?
Yeah, more calories consumed live longer.
Yeah, it seems to be telling. The fact that it's a positive association here, an upward trend, it seems to be saying countries where people eat more than average correspond to countries where people live longer. In other words, eating more makes you live longer? Is that true?
Correlation without causation.
Yeah, not necessarily. Just because you see this positive association does not mean that eating more causes you to live longer. Now, I think eating sufficient calories and getting sufficient vitamins and minerals is certainly a prerequisite toward growing up healthy. However, eating more does not necessarily make you live longer. And in fact, I've read news reports, lots of them, that say eating less makes you live longer. Huh? How does that jive with this? How can that possibly be the case if we get this graph? Any ideas?
A lot of other factors.
A lot of other factors, like?
Like living conditions, wealth, things like that.
Exactly. Living conditions, wealth of the country affects the living conditions. It affects the healthcare system. It affects sanitation. There's lots of other lurking variables that are hidden that could be the true cause for this positive association. It does not necessarily mean eating more makes you live longer. Okay, correlation does not imply causation. That's a big phrase in statistics that every stats teacher says at some point. They will say it a number of times. All right, you've got to think about those kinds of things. Lurking variables are confounding. They're messing up all these results, making us think there's a positive correlation that leads to a causation, or that is reflecting a causation when there's not necessarily. When you look at scatter plots, it's just like chapter 1 with histograms and stem plots and time series. You want to take the book's philosophy, you want to look for an overall pattern, and any striking deviations from the pattern, like outliers. You want to describe the form of the pattern, its direction, and its strength. And again, an important kind of deviation is an outlier, an individual value that falls outside of the pattern. Okay? How would you do that for this particular graph? You could say the overall pattern is an upward linear trend, a positive association. Those are some words you could use. Because of the pretty wide scatter in these points, it's not a real strong relationship. Actually, in that first phrase, I said both the form and the direction. The form is it's a somewhat of a linear pattern. The direction is that it's a positive slope or a positive association. And the strength is fairly weak, not real strong. Those are different words you could use. It probably would be okay to say moderately weak or even moderately strong. Don't say strong. Don't say real strong. Don't say very strong. There's a lot of scatter to it. Are there any outliers? It seems that this point perhaps is the biggest outlier. That corresponds to a country where people eat a lot and they don't live very long at all. By the way, the strength of the correlation that you see here, which is not real strong, is made stronger than it should be perhaps if you were looking at individual people. We're looking at countries here and averaging how much people eat and how long they live. Life expectancy is an average already. And because of that averaging, you get a higher strength to this relationship than you would if you looked at individual people. How much does that person eat? How long did they live? I guess you'd look at people who had died. And somehow you kept track of their calories, or they kept track of their calories accurately over their lifetime. Okay? That would be a tough thing to do. So when you average things, you can get a stronger correlation than you would if you didn't average things. Again, we have a positive association. I already mentioned that above average values for one tend to accompany above average values for the other, and below average values tend to occur together. Up in that quadrant, those are the above average for x and y. Down in this quadrant, those are the below average for x and y. Most of the points are here and here. Very few correspond to above average for x and below average for y. And also very few correspond to below average for x and above average for y. That's what tends to happen in positive association. If it was a negative trend, a negative association, most of the points would be here and here. And above average values for one accompany below average values for the other. And vice versa. Okay? It is good to continue using critical thinking and also plan ahead. Here's a business situation where a scatter plot could be useful. In this situation, look at the variables. And by the way, it was on the slide, but I forgot to mention. The horizontal axis is typically called the explanatory variable, and the vertical axis is typically called the response variable. The idea is that the response variable responds to the explanatory variable, and the explanatory variable explains the response variable. In this situation, the explanatory variable is the number of items sold in a day at a store. And this is the gross sales. That's the response variables. This is not labeled as well as it should be. This should be, for example, in dollars. Or if it's a real big store, perhaps in hundreds of dollars. We see a positive trend here. It's stronger than the last graph that we looked at. It's a stronger positive trend. But I've added categorical information to this picture. Some of the points are dots, some of them are X's. Which ones are the weekends? What two reasons could you give for that? The X's are the weekends. What are two reasons you could give for guessing that at least?
More items are sold.
More items are sold on the weekend. People go to the store more often. And also, there are fewer X's than dots. Weekends are 2 days a week and weekdays are 5 days a week. Okay? The store is open every day. Okay, those are two things that hint at that this might be weekends and this is weekdays. What do you see when you look at it? Again, a moderately strong, positive relationship. The more you sell in number of items, the more dollars you earn. Makes sense. Makes intuitive sense. It does seem that would be a cause-effect relationship. I also happen to see that basically the weekend trend is pretty close to the weekday trend. There's a slight difference, meaning the overall trend has a slope maybe a little higher over the weekend than it is during the weekdays. If that is indeed true, that the weekend slope, the trend, is a little higher for the weekend than for the weekdays, what would that be telling you based on the meaning of the variables? What practical thing would it tell you? Think of it. The fact that the slope here is a little bit higher than here. For the trend I'm talking about. The trend is about like that and about like that. Mhm. Well, I suppose you could price things higher on weekends, that's true. You're getting close to what I'm thinking of. I'm thinking on the weekend, people buy more expensive things. The sales per item sold is really the slope, and that's a little bit bigger on weekends than it is on weekdays. So not only do they buy more, but it seems like they buy more expensive items on average. Okay, so that's useful information, isn't it? That's a practical consequence of this graph. If this was a real graph, if you owned a business, that would be a practical thing you could get out of it. You should also realize that oftentimes weak relationships are the norm. They're pretty common. Here's an example of a pretty weak relationship. It's a slight positive trend, a very weak positive trend. What is it about? Look at the labeling here. This is about, well, labeling up here, about length and severity of bear markets. Is a bear market good or bad for investors? It's bad. Bull is good, bear is bad, right? Bull market good, bear market bad. It's a bear. Okay? Duration is how long does the bear market last? How long is the downward trend in the stock market? Okay? You should realize, business majors, economics majors, that the stock market tends to fluctuate a lot, but there are upward and downward trends that can last many months. So the duration is how long the downward trend is. For example, that dot represents one bear market that had a downward trend for 15 months. 1 and 1/4 years. This one is a real long one. Maybe this is about recessions even. It could be about recessions, not just the market. And they are distinct from each other. I suppose they are saying markets here. Here's a real short one, right there, only a month or two. Severity. How bad was it? What's the decline as a percent? How much did the market go down? For example, in 2008, when the stock market crashed, if memory serves me correct, I think the bear market was about a 50% decline. It went down by about 50%. I think it was around 12,000 for the Dow, and then it crashed to around 6,000 if memory serves me correct. Okay, going based on memory. I looked at my investments, my portfolio for my retirement, and it was not good. Okay, it's rebounded here in 2015, although the past month has been bad. There's a pretty long, that's a pretty bad decline. That's a pretty severe. This was made before the Great Recession in 2008, 2009. Perhaps that's the Great Depression right there, 1929, 1930. If you know about that. That's what that one might be. Again, it lasted about 21 months. But it's a pretty weak relationship. Yes, there's a small, slight positive association between length and severities. Longer bear markets tend to mean more decline, but it's not a real strong relationship. Okay? It can go down a lot pretty fast. In fact, in 2008, it declined by 50%, I believe, over the course of a few months. Okay? Again, I'm going based on memory. I might be wrong. You can look it up. Another example, things can be nonlinear. How would you describe this one? It's a real strong, pretty strong at least, nonlinear relationship. Like that. It's not a straight line relationship. That can happen. You can have nonlinear relationships. It is a strong relationship, relatively speaking, I think. Pretty clear here. But it's nonlinear. It's up more and more, but the slope gets smaller and smaller. That's called concave down. There are outliers. Those are outliers. When you have outliers, it's often good to add that categorical information. What countries are those? The US evidently is this one there. It's not really an outlier so much. It's still within the pattern. It's a little away from the other points. It's a mild outlier. But these are definitely far from the pattern. what happens with outliers? Why do they occur? Two reasons typically. One is you made a mistake in gathering your data or plotting your data. Or secondly, it's reality and there's some other reason for it. Probably this is reality, probably this is accurate. What are the variables? Explanatory variable is GDP per person per capita in dollars. How much essentially wealth do you have per person? The response variable is the life expectancy. How long do people live on average? Probably males and females put together. You do see a positive trend here. Higher GDPs correspond to higher life expectancies. That doesn't mean money directly makes you live longer, but it's a side effect because it's a wealthier country. It can probably better healthcare system, better sanitation, that kind of thing, better food. All right. When you see there are outliers, it's good to note them. Good to note the names again, and ask why. Why are they outliers? Botswana is the most extreme outlier. What's special about that point? For the given life expectancy, which is pretty low, the GDP is pretty high. Why might that be? GDP per person. Any guesses? That actually doesn't mean the overall GDP is really high. It's a GDP per person that's pretty high. Could mean two things or the combination of those two things. Could mean a pretty small population. It could also mean pretty high GDP that comes about because, especially because the life expectancy is low, perhaps because there are a few really, really rich people and everybody's else is dirt poor. Okay? That to me indicates a pretty wide income disparity between the highest and lowest. Now that might be true for other countries too, like the US, but this is even more extreme is what this tells me. So the few really, really super rich people are enough to affect the GDP per person by a lot. But on average, people don't live very long because the vast majority of the people are really poor. Okay? That's my hypothesis. You could look into it to see if that's true. Scatterplots in the news. Getting short on time here, so I don't want to spend much time on this. And it's probably too small for you to see. The words at least. I found this in, actually it's a blog post from the New York Times site just a few days ago, here in September 2015. It's about body mass index versus body fat percentage. The upper graph is for men and the lower graph is for women. Body fat percentage is the percentage of your weight that comes from fat. And body mass index is, I forget exactly, it's related to your height and your weight. I looked it up, but I forgot what it was, the formula was. I think we'll look at the formula next time, and we'll look into this thing more deeply next time. There is an upward trend. People who have more body fat do tend to have a higher body mass index. You have a high body mass index if your weight is high relative to your height, essentially, and a low body mass index if your weight is small relative to your height. But what they were pointing out in this article, and you can click on the link when you download the PowerPoint and look at the article, is for many people the body mass index, BMI, is not a super great measure. People that are outside the trend, this says skinny fat and this says healthy obese. This corresponds to people that have a high body fat, but their BMI is small. So they're relatively thin, but they have a lot of fat still. That can happen. And this corresponds to healthy obese. They have a high body mass index. When you look at them, they look like they're a bit overweight, but they're healthy. Maybe a lot of it's muscle. Maybe they do still have good heart health, for example. Okay, their body fat is fairly low. So they got a lot of muscles, probably the most likely thing. All right, so the article is just pointing out that BMI as one number to describe how healthy somebody might be is not necessarily a great indicator for everybody. And you shouldn't expect it to be. But that's good to know as a critical consumer of data and information in articles. We can measure the strength of a linear relationship is something called the correlation. The correlation is a numerical measure of the direction and strength of a linear relationship between two variables. It's a number. It's a statistic. It's got a formula. The formula is kind of crazy looking. Yikes. Here's the formula. This formula works. It does calculate the correlation. It's not typically used in practice. In fact, software, spreadsheets, calculators are used in practice. However, it is in the book, and I do want you to know it. And it's helpful for basically one thing. It's helpful for basically trying to understand why the correlation is positive in certain situations and negative in others. I'll write it on the board, then I'm going to go to the next slide. Again, we have the technical way to write it with summations and subscripts, and the sloppy way to write it without the index of summation, without subscripts. I meant to say index of summation. The I goes from in to in there. The summation symbol should still be in there. I'll write it in the sloppy way on the board. It's called R. It's 1 over n minus 1 times the summation, the sum of a bunch of products of a bunch of fractions. You've got two variables, x and y, corresponding to data in x and y. You've got x bar and y bar, the means of those data. The mean of the x's, the mean of the y's. You've got s sub x and s sub y corresponding to the standard deviations of the x's and the y's. That's the formula. We won't use it today, but we will probably next time. We're running low on time. I was going to use it today. Focus more on the idea. Here's the idea in summary. The correlation always ends up being between -1 and 1. It's never bigger than +1, it's never less than -1. It's always between -1 and 1 in value. Values really close to +1 correspond to a very strong positive linear trend. Values really close to -1 correspond to a really strong negative linear trend with a negative slope. Values in between, close to 0, correspond to scatterplots that are either really scattered, some big cloud that doesn't have much of a trend to it, or some nonlinear trend. So this measures the strength of a linear relationship and its direction. Here's more information. Here's information in a picture. There's a correlation. Well, it says equal to 0. Probably it's close to 0 and not equal to it. It would be very rare for it to equal 0 exactly. Effectively, it's 0 there. A lot of scatter. There's a correlation that's a small negative value. By small, I mean close to 0. A lot of scatter, but a slight negative trend. Here's a correlation that's a bit stronger, but it's positive. It corresponds to 0.5. A correlation of -0.7 that's further from 0 and closer to -1 is a stronger linear trend, but in a downward direction. Here's a pretty strong positive correlation of 0.9, and a really strong negative correlation of -0.99. Okay? Don't attempt to draw those pictures, but attempt to get the basic idea in your head. If the points were exactly on a straight line with a positive slope, the correlation would be exactly +1. If the points are exactly on a straight line with a negative slope, the correlation would be exactly -1. It never gets bigger than 1 or less than -1. What if the points were on a horizontal line or a vertical line? Technically, then the correlation is undefined, actually. But that rarely occurs, so we don't worry about it. I'm going to go quickly over some facts about correlation. These are in your book, okay? And you should certainly study them and know them for example, the quiz next time. I'm going to go over them really quickly because we've got 5 minutes left. Okay? So I would suggest not writing these down right now. Just listen. First of all, there's no distinction between explanatory and response variables with correlation. What does that mean? It means you could switch around the roles of x and y. Label the x's y's and label the y's x's and do the same formula, you get the same answer. Same correlation. No distinction. The formula is symmetric in the x's and y's. You can switch around the roles. That's good to know, actually, because with regression, that will not be the case. Both variables, of course, need to be quantitative. They can't be categorical. They have to have values that you can plug into the formula. That almost goes without saying, but it's amazing how often I give true-false questions related to that, and people get it wrong. I might say the correlation between a person's age and their favorite pizza is positive. Okay, that doesn't make any sense. Okay? Their favorite pizza is categorical. There is no correlation. And there can be a relationship, but it's not a quantitative correlation in the same way. Here's something real important and kind of subtle. R stays the same even if we change measurement units, and R itself has no units. For example, if your variables represent lengths and weights, heights and weights, it doesn't matter whether you measure the height in centimeters or inches or meters or yards, whatever. And it doesn't matter whether you measure your weight in kilograms or pounds, although technically kilograms is a mass, but don't worry about that. It doesn't matter, you get the same correlation either way. That's good. That's what you would want. Basically the reason is because these fractions are standardized values. They're like z's in a sense. Take a value minus mean divided by standard deviation. And because of that, the units cancel. Positive R indicates a positive association, really linear. Negative R indicates a negative association, linear. Values close to 1 or negative 1 is a strong linear association. Values close to 0 indicate almost no linear relationship, but there could be a nonlinear relationship that could be very strong. Like the one we saw that looked like that. Correlation doesn't say anything about the strength of curve relationships, nonlinear. And it is sensitive to outliers since X bar, Y bar, SX, SY, those are all sensitive to outliers. Okay? Not done yet. Listen carefully. Deep breath. We often want to model the trend in a strong linear relationship with something called a least squares linear regression line. This is our short little introduction to this stuff. You should read about it. You're going to have 1 or 2 homework problems related to it. You've got an explanatory variable x and a response variable y, and it is essential that you make one explanatory and one response. Okay? You can't switch them around here. And say they have a good, strong linear trend. And you'd like to model that trend. You'd like to find a straight line that essentially follows the trend. You need a slope and an intercept to find equations of lines. From the data, how do you calculate that line? You find the means x bar and y bar, and the standard deviations sx and sy, and the correlation r. The least squares regression line is typically written in statistics like you see there, which is different than you get in pre-calculus. Its slope is calculated by this formula, and its intercept, vertical axis intercept, by that formula right there. These formulas are probably worth writing down. It's a little strange, different notation, right? You're used to y equals mx plus b for the equation of a line. M is the slope, b is the vertical intercept. Okay, this is a little different notation. Y, what's that thing? That's a hat. Y is wearing a hat. You call it y hat. Why do we call it y hat? I don't have time to explain today. Next time. Y hat equals b sub 0, or just b0 for short, plus b sub 1, or just b1 for short, times x. X is the independent or explanatory variable. Y is the dependent or response variable. How do you find the slope? You don't do rise over run. Why don't you do rise over run? Because you don't know what the points are that are on the line. You do know the data points that are in a scatter plot, but it's usually the case that none of those points are exactly on the line. None of them are typically exactly in the triangle. That would be very rare. So you can't do rise over run, but fortunately, once you've got these statistics, you can use this formula. And once you've got that slope, then you can use this formula to find the intercept. You can still interpret the slope as rise over run, and in fact, you can still interpret the slope as a rate of change. All these words are going to be in your reading, and they're very important to understanding the meaning of the regression line and how to use it, and how to interpret the slope, for example. So that's our little introduction. I'm going to give you a few problems related to it that you can get